Welcome to Quality Time with MoreSteam. I am your host, Dan Swartwout. Let's jump right into today's podcast that covers the topics of process modeling and discrete event simulation. Today, we are lucky enough to be joined by Dr. Lars Maaseidvaag. Lars, how are you? Welcome to the program.
I am doing great, Dan. Thank you very much. Happy to be here.
How did I do on the name?
You did great. I mean, I only get it 1 out of every 3 tries, so.
Well, we could probably spend an entire podcast talking about the ways our two names have been mispronounced over the years.
Indeed. Or we could just decide that we need to join the ranks of Sting and Cher and just go with a single first name.
Well, in the world of process improvement, you are Lars. I mean, you're a one-name notoriety, celebrity. In this world, you are Lars.
Well, okay. Small puddle, small pond, big fish, maybe. I don't know. But perhaps some process modeling at least.
Lars, before we jump in, we're going to talk today about discrete event simulation, process modeling. Before we jump into that, how about just a little bit about your background that made you a one-name celebrity in the world of quality?
Well, I guess easiest to perhaps work from current backwards. Currently part of the MoreSteam client services team, working with clients, MoreSteam clients that need assistance with their continuous improvement programs, whether it be coaching, training, or project work. And certainly the specialty area there is support of process modeling work with Process Playground. And actually, I'm in Columbus this week at MoreSteam, working and teaching the Master Black Belt Lean week, Lean and Process Modeling week. And that's good. So that's current state. Prior to that, Vice President of Product Development, Operations, something like that at MoreSteam. Had the developers working for me, or me working for them, if I'm to speak in proper Lean terms, and teaching, working with clients, and did that for about 12 years or so. Prior to that was with George Group Consulting out of Dallas, Texas. And George Group Consulting started there. It was a Lean consultancy, then became a Lean Six Sigma consultancy when Six Sigma became a thing. So I've been in the continuous improvement world primarily as a consultant, trainer, coach, more than 30 years now, getting towards 35, yeah. And education is in operations research and industrial engineering and business. And so a PhD in operations research from Illinois Institute of Technology, MBA and Masters of Engineering in Industrial Engineering Operations Research from University of Texas, Hook'em Horns. So I guess at some point we need to insert, even though you may edit it out, that I am from about 3 hours north of Columbus. And despite all statistical odds and probabilities being against it, somehow we managed to beat you guys last year.
Oh, there is. I'm going to let that one get through. I'm not going to edit that out because I'm going to replay this episode again Thanksgiving weekend this November.
Yeah. Well, it was a long dry stretch. So we from north of the border have to celebrate the few wins that we've had over the last 20 years. So we'll see how this year goes. See if we can make it 4 in a row.
For those who may not have picked up on what Lars was talking about, of course, he was talking about the greatest rivalry in all of sports, the college football rivalry between the Ohio State University and that team up north, the University of Michigan, Lars being from Ann Arbor. And they have had, it has been 2019 since the Buckeyes won that game.
It has. It's 2019, that long.
It's been that long because they didn't play in 2020. And then Ohio State has not won since then.
Wow. Okay. So we're even doing better than I thought. Normally, I have relatively little interest in college football. And the only reason that this is even a topic of discussion is because I have worked so long for a company that is in Columbus, Ohio. Otherwise, yeah,
I tell you, yeah, I'm going to play this episode again in November, and it's either going to be vindication or, oh, wow, another year. So I'm leaving it in. I'm not editing this out. And, somehow college football comes into these podcasts a little bit. Josh Howell talking a lot about Notre Dame not that long ago.
Yep.
Lars, we are excited to have you here. And I want to jump into the topic we're going to focus in today: discrete event simulation, process modeling. For someone who's never moved beyond basic process mapping, can you start by explaining what discrete event simulation is and how it differs from just drawing a flow chart of a process?
Sure. And actually, I'll step back just a few steps further and start with a quote that within the domain of continuous improvement, my favorite quote, George Box of Box-Cox Transformations: all models are wrong, some are useful, right? And a corollary to that, everything's a model. So when we first start learning about statistics, spreadsheet models, whatever it may be, in Lean Six Sigma or continuous improvement work, one of the very first things we learn about is taking the mean or the average of a set of data. That's a model. And for some of our problems that we need to solve, simply taking the mean is all we need to do. It gives us the information we need to move forward, all the insight we need to gather. We're done. We might need to enhance that a little bit and take the standard deviation as well as the mean and enhance that model a little further and gain a little bit more insight. So everything's a model. Some are useful. What our, art is within continuous improvement is through education and experience is learning to understand what model we need to apply to what situation to gain the insight we need. So moving from taking the simple average or mean of a data set all the way forward, we end up at discrete event simulation. So discrete event simulation, as you alluded to, is very much taking a value stream map and bringing it to life. Now, for those who are just scratching the surface on process mapping and value stream mapping, those are identifying the flow of work through a process, and that could be patients through a process at a hospital. It could be electronic logical items, work orders, or lab orders through a hospital, or widgets down on an assembly line. Things flow in processes, could be information, could be physical things, could be people. And our process mapping exercise is to understand all those flows and the nuance of those flows in terms of whether we need to segment our customer body into different segments based on different paths they take through a process, how long they take at different steps in the process, how long they wait at different steps in the process. All of that goes into a value stream map and documents what that process looks like at a more or less a point in time. We do tend to look or try to look at processes over time so that we're not perhaps misled by a single sample of a day that wasn't particularly normal. The next step is once we've got that data, we've characterized the process and we can say how it has been performing. What we can't say is how it might perform in the future with any type of changes. And those changes could be common cause variation or special cause variation changes. So a common question to look at might be if we have a mix change in the products we're selling. So we're a coffee store and we introduce a few new frozen espresso drinks or something like that. And they become very popular. And so our demand goes up as well as shifts. And some of our coffee drinkers become frozen espresso drinkers. Now we have greater load on the espresso machine that takes a longer time and the blender, which takes a longer time. And what's that going to do to the capacity of our people in the process to produce those drinks? What's that going to do to the lead time of our customers coming through the process? Those are difficult things to predict with our traditional toolkit of continuous improvement, Lean Six Sigma tools. Discrete event simulation brings that process map to life, and we can actually run the process and have customers walking through the door, and we can change the demand rates and have more Frappuccino orders coming in and see what happens in the process. And so that's the real key there. Discrete event simulation, so named because we define the events of interest. And so our events of interest are Customer walks through the door, customer waits in line, customer places order, customer waits for order, and whatever the baristas might do to make that order happen, right? We define what are the milestone events that we want to model, and we build that just like we would build a value stream map with blocks that represent those events. But then in discrete event simulation, we actually go ahead and start having customers walk through the door. And if the process is too slow, they're going to queue up at the queue in front of the cash register. If it's a process with enough capacity, then they're going to zip through pretty quickly. We can see all of that. And we look at the exact same statistics that we would look at in a true live process. We look at those same statistics in the model. We're looking for queue lengths. We're looking for utilizations and run times. We're looking for lead times. All of those same things we look for in a real process are exactly the same metrics and statistics we get out of a simulated process. So commonly now it's called a digital twin, right? It's to mirror reality, allow us to perform predictive experiments to see what's going to happen in the process.
I have to ask, Lars, did you process model, do discrete event simulation on this podcast interview? Because my next question was going to be, for listeners new to this concept, what's a real world example of how discrete event simulation can help improve everyday operations? Maybe something like a coffee shop or doctor's office that everyone can relate to. Did you do some predictive process modeling on this interview? Because you answered my second question before I even asked it.
Well, that wasn't too hard because everything at MoreSteam revolves around coffee, right? So as long as we stick to coffee, we know we're going to be on target and on brand. So that's easy enough. But let me give you another example. And this is an example that I helped work with this big hospital. And that was right at the beginning of COVID, when the pandemic started. We didn't have the vaccines yet. And so, but they wanted to get the researchers and staff back into the hospitals. And they had stood up a system they had, I think, 8 or 10 computers that the staff would kind of answer 3 or 4 questions on, and then based on the answers and or a random draw, be directed for testing versus allowed into the building. And so they stood up this entry mechanism and told everybody to come back, and immediately had a queue of 1,000 people in the parking lot, not socially distant or physically distant. And it was a problem. And they needed to understand what they needed to do that process in terms of whether they had enough capacity in the process, or how could they make it work without spending more money on duplicate instances of this check-in process. And so we got on a call. We built the model fairly quickly in about 4 hours. We pulled a bunch of data in terms of the amount of staff and what time of the morning we could have them come in. And we came up with a strategy for staging people to come in at different hours. And then we were able to put that strategy into the model, run it, and see whether or not we formed unacceptably long queues in the process that they had already put into place. And in less than a day, we were able to confirm that, take the results actually up to the board and demonstrate to the board that this could work. We just needed to make this adjustment. And so just like that, we had a huge operation, big hospital, doing critical work that we were able to help get back online in terms of getting people safely into the building without excessive investment in additional testing stations around the hospital, which don't know what the amount would have been, but I was told that it would have been thousands of dollars per day. So that was a fun one. It was very impactful, happened quickly. One of the keys was we had people on the call that had direct access to the data. So we were able to query and get access to the data we needed in nearly real time, which was key. And it was a relatively small, narrowly scoped process, which was consistent with what we would do in Lean Six Sigma, where we try to scope our project to a fairly narrowly defined part of the process or small process so that we can focus on that, find the root cause, and as we say, don't try to boil the ocean. A lot of what I see in simulation is trying to make very grandiose, large models that model the entire Atlanta airport or something like that, right? And to what end? It might look nice, but it's not going to actually help you solve any particular problem at any point in that process. So,
Lars, you did it again,
oh,
because this was my next question. Your COVID-19 hospital project reduced queue times without major investments. Can you walk us through how simulation revealed solutions that traditional lean tools might have missed? So you did it again. I'm going to have to ask, what's my next question going to be, Lars?
let's see. Huh. How do you go about learning how to do this?
No, okay. All right.
Oh,
We
okay.
finally, but I do want to know, can you walk us through with that project? Can you walk us through how simulation revealed solutions that traditional lean tools might have missed? Is there something you can add to that we already talked about that project?
Sure. And the idea here is that when we're doing traditional continuous improvement work, we have our set of tools, and those tools are primarily descriptive in terms of telling us how things have been or how things are now. They don't give us much support in the way of predicting how things might work in the future. And they certainly don't allow us to experiment with different visions of the future, right? So we always talk about generating multiple different improvement concepts, perhaps putting them on a prioritization matrix, right? To figure out which concept, a Q matrix, right? To figure out which concept might be the best concept to go forward with. But a lot of that still leaves a lot of room for not really knowing how that solution might actually work, but rather just hypothesizing how it might work. And therefore, we tend to not, we might go up to the edges of the box, but we still keep ourselves in the box. With simulation modeling, we can step outside that box and really try some wild ideas that are perhaps quite a bit different, certainly more daring than we might attempt in an actual live pilot of an improvement. And so we can try some of those out of the box solutions and just think about different things and test them out very quickly and see if that's even a direction to think, right? And so it's up that ideation and hypothesis testing. It's still not perfect, right? It's subject to what we call extrapolation error, because we're extrapolating from one current state to a future state that may or may not operate as modeled, right? But we're hopefully close. And so in this case, we looked at the system they had set up and the physical spacing that they allowed in the system in terms of queues to form and the number of resources they had and the number of hours they were operating that. And all of that seemed fine on average. And so for the 5 hours or so that they were standing this up in the morning for staff to come in, if you did the traditional lean method of just looking at capacity, you'd look at the hours of capacity, you'd look at the hours of demand and say, okay, on average, we're great. This should work. The problem was all about when the demand was actually coming, right? And so this is a dynamic problem that all businesses face, whether it be the coffee shop with a morning rush hour or whatever. Businesses very rarely get to face perfectly stable demand. There is seasonal demand. There's seasonality within the month, within the week, within the hour, whatever it may be. Demand tends to be dynamic. And with that dynamic demand, one of our traditional approaches is to say, okay, let's take a look at peak demand and do all of our traditional Lean Six Sigma tools at peak demand. And then let's do them at the low demand and maybe the shoulder period and do separate analyses at different points in time and say, at peak demand, we do have enough capacity to do this. At low demand, we've got way too much capacity and this is what our staffing plan should be or whatever it may be. None of that tells us what the transitions between those periods look like, right? And so what's the transition into peak demand? What's the transition out of peak demand? And that's what we're able to see with the simulations because they're all about the interactions. A basic premise in most of our statistical tools is in academic lingo, it's IID, independent and identically distributed, or what we say in Six Sigma is constant variance. But the idea that everything that happens is independent, therefore random, compared to the thing before it, that's not reality. If If you and I go into a coffee shop and I'm taking a whole lot of time trying to figure out what to order, you get to suffer my indecision behind me in the queue, right?
When somebody takes too long like that, I'm thinking, are you applying for a job? What's going on up here?
Right, right. So that's the thing. Life is all about interdependencies, right? And a lot of our statistical tools assume randomness and independence of events. Simulation modeling, discrete event simulation model, is all about understanding those interdependencies and those interactions. And that's what is the key part that really differentiates it from our traditional book of tools. As companies, organizations, hospitals, whatever, complexity is just getting worse. Nothing's getting simpler, right? The menus are getting larger and more diverse. The product offerings are getting larger and more diverse. Whatever, every place, more complexity, more mix variation, more variation because we have to be trained in how to prepare 85 different coffee drinks versus 3, right? And so variation increases both from having to read instructions on how to do the 83 we don't know how to do off the top of our head, and then just the mix variation. So all of our organizations deal with so much more variation, whether it's regular, what we call common cause variation, just in how long it takes to pour a cup of coffee, or mix variation that's induced by the mix of our products or services we sell. That's the big one. And then special cause variation, where it's a rainy day and we sell a lot more umbrellas. So we have all these sources of variation. They're only getting worse. There's only a few companies that are in the lucky position of kind of conquered that complexity. And they do that through, a long-term strategy of, we're not going to offer a lot of complexity. And the trade-off there is we're going to offer great durability, reliability, whatever it may be, right? And so what comes to mind is Subaru. There's only a few models of Subarus and 2 or 3 total different engines in the entire model lineup. And so not a lot of complexity, not a lot of variety of choice if you're going to buy a Subaru. You've got a couple degrees of freedom and that's it. Versus if you're going to buy a Ford or a Dodge or something like that, you've got a lot of different choices, a lot of different colors, all this variety. That variety comes at the cost of both managing that whole process, trying to make that in a reliable fashion, complexity cost, and understanding complexity is very challenging. It's outside the domain of our traditional Lean Six Sigma continuous improvement tools. And that's where this type of discrete simulation process modeling comes into play. It's all about understanding those interactions, those interdependencies.
When you were talking about interdependencies, I'm not exactly sure why, but my mind immediately went to blackjack. Because if you're playing perfect blackjack and somebody at the end of the table hits on 17 and ruins the table for everyone, there's your interdependency right there.
Absolutely, right? And in thinking about blackjack too, it's, what is it? The number of decks of cards you use, isn't that called the shoe or the shoot or something like that? So if you're single deck blackjack, then that interdependency is only stronger because they just consumed one of the 4 cards that I really needed, right? If you're in a 6 deck shoot or shoe or whatever it's called, then that interdependency becomes a little less critical because there's a lot more of those, that jack that you needed or that ace that you needed available. So that the level of interdependency definitely has a relationship to the volume of transactions, right? Lower volume, higher effort, more complex transactions are more easily going to impact the next person in the line, right? Versus very high frequency, high speed transactions, McDonald's or something like that, you're less likely to get badly impacted, both because there's parallel paths to get through the process, as well as it's just a less complex process that's designed for higher volume, higher frequency, higher speed. So all of that comes into play, and things that we need to think about when we're looking at designing and improving processes, all that needs to be thought about. And in the abstract, we can think about it and say, well, it should do this or it should do that. this process modeling allows us to just step it up a notch and say, within the bounds of the error of how we built our model and what we are using to base our model, and knowing that real future might be a little bit different, within that tolerable error, we can start to predict what these impacts are going to be. And that's the real power.
Lars, obviously, with your time here at MoreSteam, very instrumental in Process Playground, very instrumental in EngineRoom. How does Process Playground make discrete event simulation accessible for teams without advanced programming skills? And how does Process Playground integrate with the other Lean Six Sigma tools in EngineRoom?
Good question. So my background being largely industrial engineering, the first sort of commercial grade simulator that I used was called Extend. Now I think it's called Extend Sim. And I've always said that these simulators, and they're very powerful simulators, they're very expensive simulators, they are designed by industrial engineers for industrial engineers. And so the learning curve is fairly steep. The prices are $3,000-$4,000 up per seat, all the way up to one that I saw was $100,000 for a single license. Yeah.
Wow.
Yeah. And you needed to know object-oriented programming to pull your queue length out of your model in that $100,000 program. So they are very powerful. Some of them have incredible 3D graphic engines associated with them, so that all of the state variables of your discrete event simulation drive graphics. So you've probably seen sometime, little news clips of the Atlanta airport model showing all the little people running around and going through the TSA pre-check or whatever and out to the gate. And those graphical models are typically built on discrete event simulation models running underneath with these powerful graphics engines. So really powerful tools, can model anything in the world. But the learning curve is steep and intense. And just like programmers kind of speak a different language, and if you speak that language, you're definitely better off in life right now. Engineers, the same thing, right? They speak their own language, and if you speak it, fine. But if you don't, it's going to be challenging. So what we tried to do with Process Playground is create a user experience that was more similar to value stream mapping than simulation modeling through the traditional tools, to really make it, and not just drag and drop. Most of them are drag and drop to a fairly big degree, but to just make it much more straightforward and easy to get up to speed. With Process Playground, we have a training course called Kathy's Best Worst, named for our former vice president of sales, and our joking about her retirement plan, selling bratwurst at the Milwaukee State Fair or whatever. So I don't know if you heard that story, Dan.
I have heard that story. And didn't Kathy work at Johnsonville for a time?
She did. Yeah. So there was, there was always bratwurst in the conversation somewhere there.
Guess what I made for dinner last night, Lars? You process modeled me to a T. I had bratwurst for dinner last night.
Cheesy brats, spicy brats, or regular brats?
Beer brats.
Beer brats, regular brats. Okay. Anyway, fairly quick, within a day, you're up and building functional models in Process Playground and understanding how the technology basically works. Now that's the basics of it, but this is an art as well. And that art largely revolves around seeing your process and seeing the tools that you have available in Process Playground and envisioning how to fit your process in with those building blocks you have, right? So you've only got a certain number of Lego bricks, and from those Lego bricks, you have to build your process, build your car, right? And actually, I've never used that analogy or that metaphor before, but this works. Back in our young days, I certainly had a big box of Legos. I imagine you did as well. And we take our Legos. And back then, they were all just square blocks.
I even had Duplos, like little kid Legos.
Okay, the bigger ones, yeah. And so we'd click our Legos together and we'd build something that approximated looking like a car.
Mm-hmm.
Its edges were a little too square and a little too pointy and whatever. And there are always those annoying little extra dots on the paint job on the top, right? But we built something that looked pretty much like a car. And that actually is a pretty good metaphor for modeling because we're not going to ever be able to perfectly match reality. Humans, especially, tend to not operate in nice continuous distribution ways, right?
Certainly.
We get interrupted, we do things in inconsistent ways, and so it's difficult to model human behavior, but we can get close enough that the car built out of our fixed Lego blocks that we have available to us looks enough like a car that we can operate it and we can answer some questions about that car. Same idea here, right? We have a fixed number of blocks in Process Playground that perform different functions. And it's a bit of an art as well as a science to string those together and build our process map that looks enough like reality. Back to George Box's quote, all models are wrong, some are useful.
Some are useful. Also, the title of a Street Stats episode on YouTube with Kevin Keller.
Excellent. All right. Yep. Best quote ever. And Kevin is a champion at this process modeling as well. And he was thrilled when he saw Process Playground because some of the problems that he tried to solve earlier in his career, knowing that he needed some tool to manage these dynamic interactions, but being frustrated earlier in his career at not having a tool to do that, when he saw Process Playground, it's like, where has this been my whole life? And it's been hidden away in the vaults of the industrial engineers, right?
High barrier of entry is what you're saying.
High barrier of entry. Yes, indeed.
Thanks, Lars. In contrast, there is a low barrier of entry to this short break. MoreSteam's enterprise process improvement platform includes the tools, training, and software you need to transform your organization into a problem-solving powerhouse. Join the ranks of Fortune 500 companies that trust MoreSteam for their enterprise process improvement. Visit MoreSteam.com to learn more. Also, I want to take just a moment to thank you for listening to Quality Time with MoreSteam. You can email the show at qualitytime@moresteam.com. And if you're enjoying the show, please leave a rating or review on your favorite podcast service. And now back to my conversation with Dr. Lars Maaseidvaag. Lars, what are, obviously you know this as well as anyone, what are some common pitfalls when building a process model? And how can practitioners validate their simulations for accuracy without getting overwhelmed?
Yes. Analysis paralysis is the term we use, where we get kind of stuck, either worrying about or just overanalyzing things. And analysis paralysis can explode even worse when we're building these process models because they're inherently open-ended. There's no done point. Just like value stream mapping, though, it's a top-down hierarchical methodology. We're going to start with a high-level view of our process. And by high level, I mean we might have a single activity block that represents, back to the coffee shop, the entire production and delivery of a cup of coffee as a single entity that just says, okay, it's on average going to take a minute and a half with a standard deviation of 30 seconds. And it's a single block. And then as we're working on our value stream map, we might say, well, sometimes in that single block that represents that whole coffee production process, we do have some problems and we have some defects. And so maybe we need to break that single block down into, and so this is the top down. We've got a single process map up here, single block, make coffee. We take that single block and we pull it down here and we explode it out into a micro map of that process, right? And now we're looking at all the individual steps of maybe it's, put the beans in the grinder, grind the beans, run the espresso machine, and we map that out. And then maybe we find out, well, the espresso machine, it only runs 50% of the time. And so we need to map out the detailed process down another level of exactly what sequence of buttons you need to press in order to make the espresso machine run. And so we keep driving down in our mapping exercise to get to the level of detail we need to see where the problems and the root causes of our problems reside. We can't be too high or we won't see them. We have to dive down. But what we don't want to do is dive down everywhere and map at super low level of detail every aspect of every process. We'd be doing a lot of excess processing work. And that's the one, for those that know the 7 or 8 wastes in our lean world, excess processing is one of those wastes. And that's the one that we continuous improvement people are guilty of. Excess processing, going too deep in too many places instead of maintaining focus on where we're seeing problems and deep diving there only. And that is one way to help avoid the analysis paralysis. It's also what you have to do in building these models is stay very focused and stay as narrowly focused as possible. And the reason you want to do that is these models require data. We have to collect data on how long every aspect of the process takes, how long the queues are, what the different types of customers flowing through, all that data we need. These are data hungry models. And if we expand our scope too much, we're going to have a data collection plan that would absolutely sink a battleship, right? And so we want to have a data collection plan that's only going to sink a rowboat. So that's the biggest error that is made, is scoping it too big and not staying focused. Stay very focused on where the problems are happening. Drill down both in your value stream mapping as well as in your model building to the level you need to give you the detail you need. An example from the MBB class, Master Black Belt class that I'm teaching this week. One of the examples we use is managing the queue length of a ride for a roller coaster at an amusement park. And the goal is, current state is, the queue time is about 30 minutes. The goal is to get it to 10 minutes or less. I know that's make-believe. It's a mythical amusement park that actually operates in minutes rather than hours. But the model we have to build is, well, we have to see, of course, what our demand is in terms of how many customers are coming in to ride that ride and how long it takes for that capacity of the train to be consumed. And so it's a 3-minute fixed ride around, and then it's a variable amount of time depending on the number of people that actually are getting on that train for that ride, that set of cars. Now, what doesn't matter is how we account for that time, that total amount of time of getting on, taking the ride, and getting off. And so we can conveniently model it by actually putting the load and unload time together as processing time per person and putting setup time of 3 minutes in front of that as the time it takes to actually run around the track, all in one block. Now, that's not how reality happens. Reality happens as load, ride, unload. But since the question we're trying to answer is, what's the queue time in front of that? I don't need to model in detail the load, ride, and unload. Let's just put that as a single black box, because that single black box is going to have the same impact on the queue time, whether I do it as a single black box or as a detailed 48-step long process of getting you and me squeezing onto a roller coaster while our kids are zipping in and out, right? So no need to model that deep detail of actually getting in and out of the ride. I just need to model the total time consumption for that. So that's the idea, right? You need to know the questions you want to answer in order to know the depth that you need to model and the detail that you need to have in that model.
I've been on a lot of roller coasters in my life, Lars, and just you've really opened my eyes to thinking a lot about a lot of things, because like for our conversation, I've been on a lot of roller coasters in my life. And as I've been close to the roller coaster near the end of the line, I was just thinking about all of the variabilities that could come in. Somebody decides they don't want to ride it after all. They get on, it's too scary, so they want to get off because it's too scary after all. Somebody who can't figure out how to fit into the ride, how to pull down the bar. Maybe I have a hat and I have to strap it to something and somebody tells me to take it off. There's so many variabilities. How do you account for that? I mean, how do you account for that if you're putting everything in that box?
And so that's another perfect example of how much detail do we need to get into. If the problem we're trying to solve is how to speed up that loading process, then we need to go into a deep detail on that, right? And we need to say, okay, 20% of our people are going to have hats. So we have a decision block, has hat, yes or no? And if yes, then they incur time to fasten hat onto strap, right? And that all adds to the delay of getting loaded. And, if I'm a pretty tall person, pretty big person, I get into some of these roller coasters and it's a struggle to get that bar clamped down on top of me.
Absolutely. I've had to see they come and there's multiple people pushing the bar down.
Yeah. And then I'm, not a high level of confidence on how well that thing's latched at that point, right?
Action park. Now we're talking action park.
So if the root cause of our problem, or if the problem we're trying to solve is the time that it takes to load our 12 people onto the roller coaster is longer than what our specification is, or whatever that specification comes from, the voice of the business, right? In that case, then we're going to have to model all those little detailed bits of time based on the mix of you and me versus our children trying to get our children in and out in no time, right? We're hoppling along trying to figure out how to do it. But if that's not the focus, if the focus is just let's look at how long that queue is and whether or not we have enough capacity in terms of trains that we're running, we don't need all that detail. We can just use a single distribution of time, random distribution, that is going to have longer tails to say, okay, here's the Dan and Lars, the long ones. Here's our sons, quick ones, and here's the right. And so we can take all that noise from all the different aspects of the loading process and just encompass it into a distribution that has a bigger spread of variation. We'll study our actual data to define that distribution, but we'll just use a bigger distribution, a bigger spread of a distribution to define that variation and call it good, because that is all the detail we need there, because we're trying to solve a problem over here. Later on, if we're focused on just solving that problem of how to actually speed up that load and unload process, that's a different model. And we're actually not concerned with the queue over here. We're just building a model and looking just at that load and unload process, right? And all comes back to what are we trying to gain insight into, focus our modeling, focus all of our continuous improvement work on answering that question.
And again, it goes back to the quote. All models are wrong, some are useful. Because if you're just giving this standard time for when people are getting on and off the roller coaster, it's not going to be right, but it could be very useful.
It's right on average.
Lars, this has been such a great conversation. Thank you so much. I will have all of your contact information in the show notes. Great topic. I learned a lot. I'm sure our listeners learned a lot. And it has been great to see you back here in the halls of MoreSteam HQ in your favorite city, Columbus, Ohio.
I do love Columbus, Ohio, I have to say.
Lars, will you join us again sometime in the future to discuss, obviously, you are Dr. Lars, you are Cher, you are Sting, you are Lars. So many areas of expertise that you have. I'd love to have you on the show again to tackle another specific area of quality and continuous improvement. I hope you'll join us again in the future.
Absolutely, anytime. This is a lot of fun, so happy to do it monthly if you can come up with enough topics.
All right, well, great. Thank you so much, Lars. I appreciate it.
All right, thanks, Dan.
We'll be back in 2 weeks with more quality time with MoreSteam. Thanks again.